Welcome to a special edition of Physics Podcasts here. We're going to be taking a look at this constant acceleration worksheet that you did in class yesterday. Starting with question number 1, we've got this graph, and the first question asks us to describe in words the motion of the object from 0 to 6 seconds. Now, this is a position versus time graph, so this graph is literally telling us where the object is at each point in time. So for instance, if I were to take this point right here, this is t equals 1 second, and this is x equals 0 meters. So that means that according to this graph, at 1 second, the object is at 0 meters. If I continue forward, at 4 seconds, the object is at, well, this goes up to 25 and 5, so each of these is 5 meters. So that means this is at 15 meters in 4 seconds. So if we're describing in words the motion of the object, that means it's going to, from 0 to 2 seconds, be stationary. So from 0 to 2 seconds, it's stationary. And then from 2 to 6 seconds, what happens? Well, at 2 seconds right here, it starts to move. Right, it starts to move. Now, how fast is it moving? Well, we know that from 2 seconds to 6 seconds, it goes up 30 meters, and it goes over 4 seconds, right? Because it goes up 30 in 4 seconds. So this corresponds to a velocity of 7.5 meters per second. So it's at 2 seconds it starts to move at 7.5 meters per second, and is moving at a constant velocity. And how do we know it's a constant velocity? Well, if you take a look at the line here, the line is not curving, it's a diagonal line, which means that the slope of that line is constant. And when the slope of a line on a position versus time graph is constant, that means that our velocity is constant. Because remember, we're relating x, v, and a like this, where we're taking slope going to the right, and we're taking area to the left. And I'm going to go ahead and just copy this so we can, oops, not that though. I'll go ahead and copy this so that we can play with it later on. I did say to ignore question B. If you were interested, it would look something like this. It would be stationary for a little bit of time, and then it would start to move at a constant rate. But as I mentioned in class, we're not going to be talking about motion maps. So the instantaneous velocity, this is where we get a little bit confused with the wording. Instantaneous velocity is the velocity at some time. Now, to figure out what the instantaneous velocity is, we take the slope of the graph at that time. So if we're looking at 1 second, up here at 1 second, well, 1 second is right here. And so the question is, what's the slope of the line at that point in time? Well, it's a horizontal line, and so the slope of a horizontal line is 0. Right, 0 meters per second is the slope of that line right there. Then we're looking at 3 seconds, so here's 1, here's 2, here's 3 seconds. And at 3 seconds, what is that? Well, this point right here is part of a much bigger line, which is this line right here. Right? So the question is, what's the slope of this line up here? Well, we already figured that one out, because we know that on this part of the line here, we went up 30 meters, and we went over 4 seconds. So if the slope of this line is then 7.5 meters per second, then that means that at 3 seconds we're actually traveling 7.5 meters per second. The next part's asking about the simple average. Simple average is just taking the two numbers, adding them up, and dividing by 2. So we have 0 and 7.5. We add them together, divide by 2, and we get 3.75 meters per second. Then the average velocity for the entire interval then. Average velocity, we said, is the total displacement divided by the total time. And so we end at 30, we started at 0, and it took us 6 seconds to do that. So we end up with a speed, or an average velocity, of 5 meters per second. So our simple average, 3.75 meters per second. Our average velocity is 5 meters per second. The two values are different then because of the weighting. Because when we look at the graph up here, it is not proportional. We're traveling at 0 meters per second for 2 seconds and then 7.5 meters per second for 4 seconds. So it's not equal timing. So if they were equal timing, then these two averages would be the same. The best way to describe the motion of the object likely is going to be this average velocity right here, because it does take into account the weighting of the objects. So this is the best right here, because it does take into account the fact that we're traveling at 0 and then traveling at 7.5. Now we're asked to then graphically represent the relationship between velocity and time for the object. And if we remember actually I have this copied. Let's paste that. There we go. If we have this right here, we know that then the velocity is created from taking the slope of the position graph. And on the position graph, our slope is 0, and then our slope is 7.5. So for the first 2 seconds, we're traveling at 0 meters per second. And then, let's just label these 2, 4, 6, and 8. Then for the next 4 seconds, we're traveling at 7.5 meters per second. So that's going to look like something like that as a line. And again, you can have dashed lines, open circles, whatever you want. So there it is. It travels at 0 meters per second for 2 seconds, and then it travels at 7.5 meters per second for 4 seconds. And then we're asked to determine the total displacement of the object. Now we know from the other graph what this should be. It should be 30 meters. But let's show that we can get that from this graph. To go from velocity to position, we're taking the area. So what area would that be? Well, it's the area underneath the velocity graph, between the velocity graph and the x-axis. So that is this blue shaded area right up here. This blue shaded area is a rectangle, and the area of a rectangle is base times height. Our base is 4 seconds, and our height is 7.5 meters per second. So 4 times 7.5 is 30. There we go. For the next question, we have an object that is clearly not going at a constant velocity, but it's also not disjointed. It's kind of smoothly curving through. So we're asked at what point in the graph is the object moving most slowly. And the trick for this is that we have two extremes of how fast an object is moving. We have a horizontal line and a vertical line. Now, a horizontal line is slope of 0, which means that a horizontal line is showing very slow motion. On the other hand, a vertical line has a slope that's undefined, or I'll say equal to infinity, just don't show your math teachers, which means it's moving very fast, right? Because the slope, again, here we go, the slope of our position graph gives us velocity. So the question is, at what point above is the graph moving most slowly? We're looking for where the graph is most horizontal, and that would be at B and at F, because it's most horizontal. When it's speeding up, that means it's going from horizontal to vertical. So where is the graph going from horizontal to vertical? We see from B, it's pretty horizontal, and then C, it gets more vertical, and D, it gets even more vertical. So I would say one interval would be B all the way to D, and then from F up to G, I would also say it's getting more vertical because it's very horizontal at F, and it's more vertical at G. Then the intervals where it's slowing down are the intervals where it's going from vertical to horizontal. So slowing down, I would say, would be A to B, because it's pretty vertical here at A, and it gets more horizontal at B. And then I would say D to F, it's also slowing down, because it's pretty vertical at D and less so at F. So A to B, and then D to F, and it's going from vertical to horizontal. And the final question here is, at what points on the graph is the object changing direction, and how do you know? It changes direction when it moves from forward to backward, or backward to forward. Now, forward to backward means it's going to be moving up as it moves to the right, and then moving down as it moves to the right. So if we take a look, along here it starts to move up, and then it's starting to move down. So somewhere between it had to stop and turn around, and that point where it's turning around is B. Then later on it's moving down as it goes to the right, and then up as it goes to the right, and so at F it's also turning around. So B and F. The final page in here, we've got a stunt car driver testing the use of airbags. We know that it's a constant speed of 25 meters per second for 100 meters. They apply the brakes and they get to stop just before a wall 50 meters away. So qualitative position versus time graph. Remember, qualitative means that we're not doing anything with numbers. So what's happening? Well, it's a constant speed at first, and then they're slowing down, right? Accelerating uniformly to a stop. So in general, what that's going to look like is, and it doesn't matter where you put this on the vertical axis, you're going to be going in a constant, you're going to be increasing your position in a constant way, right? Because they're traveling forward at a constant speed, and a diagonal line represents constant speed. And then you're accelerating uniformly to a stop. So you're still moving forward, but you're just moving forward slightly slower, and then slightly slower, and then eventually coming to a stop. So something like that. So then we would see that this area here, to the left of the dashed line, represents the constant speed, and to the right of the dashed line represents the slowing down. Okay, because you're still moving forward. For the velocity then, we know we have a constant speed, so we're going to have a horizontal line for the first little bit of time. And then it's going to slow down uniformly, which means our speed, our velocity, is decreasing until it gets to 0. Okay, and again, we could break this up. We've got to the left of the line, I'll have to scoot that over, to the left of the line is where we are traveling constantly, and to the right of the line is where we're slowing down. So the first question is, how long does it take for the car to travel the first 100 meters? Well, we know it's traveling 100 meters. Let's get rid of that. It's traveling 100 meters at 25 meters per second. So every second it's traveling 25 meters. So the question is, how many seconds does it take to travel 100? Well, after 1 second, we'll have traveled 25. After 2 seconds, we're at 50. 3, we're at 75. So the answer therefore is 4 seconds, because after 4 seconds, we've traveled 25 meters per second for 4 seconds, and we get 100 meters. Then it tells us to remember that the area underneath the velocity versus time graph excuse me, is the displacement of the car. So that means that this area here is the displacement of the car when it is slowing down, right? Because this is our slowing down part. And so we know that it needs to come to a stop in 50 meters, so our area has to be equal to 50 meters. This is a triangle, so our area is 1/2 base times height also. And we don't know how big the base is, but we do know how big that height is, because this constant velocity here is 25 meters per second. So really what we're saying is that 50 has to be equal to 1/2 our base times 25. And when you do the math out there, you should get that our base is equal to 4, which means that our time is equal to 4 seconds. Okay. Now we know the time of travel, so we can sketch a quantitative velocity versus time graph. So let's go with each of these being 5. So 5, 10, 15, 20. Here's 25 right here. And we're going to go across for 4 seconds. Here's 4 seconds. And then here's 8 seconds. And then during that time here, we're now going straight down to 8 seconds. And so that's our quantitative velocity versus time graph, because we've got 25 meters per second here, 4 seconds, 8 seconds here. The final question is, what acceleration is provided by the brakes, and how do we know? The acceleration is only provided by the brakes during this part of the trip. And the acceleration then, on a velocity versus time graph, is the slope. So our slope, in this case, is our v final minus v initial divided by our final time minus our initial time. And so our final velocity is 0, our initial velocity is 25, our final time is 8, and our initial time is 4. So we end up with negative 25 over 4 meters per second squared. Meters per second squared, which is equal to 6.25 meters per second squared, and that's negative. Okay, and we know because, again, the slope of our velocity versus time graph gives us the acceleration. That's it for the video. Thanks.